going to be finishing the lesson today. We only have a few left, and then we're finished with 2-1. 5, but we're not going to do one of them because one of them, 2.2, is verifying, and just time-wise, we're going to just move on because it's not a whole lot to it. It's more or less showing that, let's see here, yeah, I can't think of any off the top of my head, but they'll give us an equation and we have to show that it is true. We have to show that these do work out to be the same thing. That tangent of x then times cosecant of x is equal to secant of x. So we have to show that this is true, and to do that, well, we know that tangent is sine of x over cosine of x. Cosecant of x is 1 over sine of x, and we can't use anything across the equal sign. We've got to show the left side's equal to the right. Well, those would simplify out, leaving us with 1 over cosine of x. Well, cosine of 1 over cosine of x is secant of x, therefore we verified that it's true. And that's the whole chapter, or that whole section. And I don't see a whole lot of reason to go into it because we're just proving the left side's the same as the right. That's part of the reason why before it kind of got, we were going to do it before fall break because we had those 2 days. It wouldn't have made a big difference if you remembered after fall break. But I'm just going to remove it. Not hugely important. Does that make sense? Okay. So what we want to do here is we want to solve using the given information. We're told that tangent is equal to x is equal to 2 tangent of alpha, and alpha is between 0 and pi over 2. We want to find out what the square root of 4 plus x squared is, and simplify if possible. Well, we're going to replace x squared with what we were told it was equal to, or x with what we're told is equal to. We're told that x is equal to 2 tangent of alpha. Now, since we have 2 tangent of alpha squared, we can multiply it by itself. So we don't have a plus sign or minus sign between the 2 and alpha, so we can just square both terms. Our 2 squared is 4, and we get tangent squared of alpha. Whenever we see tangent squared, secant squared, cosine squared, sine squared, any of these trigonometric functions squared, we're trying to solve, we're trying to simplify, we're coming back to the Pythagorean identities. And since we have tangent, this is the one I'm going to look at. 1 plus tangent squared equals secant squared. Okay. That's kind of nice to know. Okay, there we go. So we get this here. Now, I'm writing it here as just a reminder to myself. This is what we have. Well, now the question is, how can we get these two to match up? Because we need to rewrite this, or be able to rewrite this part as 1 plus tangent squared. Because if we can replace it as secant squared. Now, probably the other question is why? Well, whenever we simplify a square root, because that's kind of what we're trying to do, we're wanting to simplify the radical if possible. And the only way I can simplify a radical is if, especially with a square root, I have something inside of it squared. But the plus sign's what's really throwing a wrench in all of this. Because I need one term or just multiplication where we can split it apart. Now, looking at this here, because if, I'm kind of backtracking just for a second, if I could somehow rewrite this 4 plus 4 tangent squared of alpha as 1 plus tangent squared of alpha, then I could replace this 1 plus tangent squared of alpha with just the single secant squared. Because if I can do that, then it's going to make everything easier. Well, what's in common with the 4 and 4 tangent squared? The 4, yes? So we can factor it out of both terms, leaving us with 1 plus tangent squared of alpha. And as we just said, 1 plus tangent squared of alpha is the same as secant squared of alpha. So I can replace it with well, now it's a little bit easier to simplify this because we have two things multiplied together, and according to radicals, we can break multiplication up. Because the square root of a times b is equal to the square root of a times the square root of b. This is just properties of radicals. So all the square root of 4 is 2. Square root of secant squared is just secant of alpha. Excuse me. And that's it. Questions on this here? And hopefully, as you notice with these here, it's mainly just manipulating the equation into something we can use and then reducing. We'll do a similar thing here. So we have 9 minus x squared. Well, it's going to be 9 minus 3 sine of alpha squared. So we place x with 3 sine of alpha squared. Now we can square it since it's an individual term. Our 3 squared would be 9. Our sine squared is sine squared. Since they both have a 9 in common, I'm going to factor it out. Giving us this here. Now, according to Pythagorean identities, sine squared of alpha plus cosine squared of alpha is equal to 1. If we wanted to solve this for cosine, we would subtract sine from both sides, telling us cosine squared of alpha is equal to 1 minus sine squared of alpha. Well, that is kind of helpful because we do have 1 minus sine squared of alpha, so we can replace it with cosine squared of alpha. Now, just like the last one, we could split this up, but we don't necessarily have to, because the square root of 9 would be 3, square root of cosine squared would just be cosine. because since we have it as one term, now instead of two terms being added or subtracted, we can just take the square root of it. And that's it. Questions on this here? We ready for the next one? And I believe these are the last types. Simplifying the expression, adding or subtracting rational expressions. Now, to be able to add or subtract rational expressions, we have to have the denominators be the same. Now, this one's kind of nice because the left side's denominator has 1 plus cosine of alpha. So I'm going to multiply 1 plus cosine of alpha on the right. The one on the left needs to have a sine of alpha. The one on the right had 1 plus cosine of alpha. The one on the left doesn't have it. The one on the left has sine of alpha. The one on the right doesn't have it. So we're going to multiply that on both sides. Now, the interesting thing with the denominators, we just need them to be the same. So we don't actually need to multiply through. If we do need to do that later, we can, but most likely it's not going to be necessary, because as long as the denominators are the same, we can add the numerators. There is no combining of like terms in the bottom of the fraction, so there's not a necessity to multiply through. Does that make sense? Now, the numerator, we will have to combine like terms. We're going to have to use addition and subtraction depending on the signs and what we have. Now, if we look at the left, we have sine times sine, which is sine squared of alpha. On the right, we'll have to distribute the cosine. Cosine times 1 is cosine of alpha. Cosine times cosine is cosine squared of alpha. Questions on how we got to this here? Now we can add these together. And we're going to say we have sine squared of alpha. Plus, I'm going to move the cosine squared of alpha over next to it. Plus cosine of alpha. Any questions on how we got to this point here? Now, this is not in simplified form, unfortunately. And there is a reason for it. We'll deal with it later. And that's part of it is the numerator. I'm going to get a highlight. This part here. Because we have cosine squared plus sine squared. Well, according to the Pythagorean identities, cosine squared plus sine squared was equal to 1. Questions on anything we've done so far? Now, there is something interesting, yes? Because what do we have now? We don't have the extra parentheses, but we have 1 plus cosine of alpha on top. We have it on bottom, yes? So we have 1 over sine of alpha. And if we want to get this really simplified, this is the same as cosecant of alpha. The sine of alpha is equal to 1 over cosecant, and cosecant is equal to 1 over sine. So we're able to take those two fractions and actually reduce it to cosecant. Questions on this here? And that right there is part of, would have been part of 2-2, is that it would have started off by saying that this is equal to cosecant of alpha, prove that this is true. So then we'd have to go through this entire process again just to show that it is this. Any questions on this here? We're ready for the next one. Simplify. So to simplify this, we need to be able to add these two fractions together. But in order to add them together, we need the denominators to be the same. So for the one on the left, I'm going to multiply it by 1 minus sine of alpha. And on the one on the right, I'm going to multiply by 1 plus sine of alpha. Now the numerators are nice. 1 minus sine of alpha times 1 is just 1 minus sine of alpha. 1 times 1 plus sine of alpha is just 1 plus sine of alpha. Just like this here. Now the denominators I would normally leave alone, but we have a difference of perfect squares. Because if I did, and I'll show you this one on the left, multiply this out, 1 times 1 would give us 1. 1 times sine of alpha is going to be plus sine of alpha. Negative sine of alpha times 1 is negative sine of alpha. And negative sine of alpha times sine of alpha is negative sine squared of alpha, which these cancel out, leaving us with 1 minus L. Yeah. Sine squared of alpha. This seems like an odd step, but it'll make sense in a minute. It's kind of weird. Now, we can add these two together, so we'd have 1 minus sine of alpha plus 1 plus sine of alpha over 1 minus sine squared of alpha. Well, here, the numerators, negative sine of alpha and positive sine of alpha, combine to become 0. Our 1 plus 1 gives us 2. As we stated a minute ago, 1 minus sine squared of alpha is the same as cosine squared of alpha. Well, 1 over cosine is the same as secant, so 1 over cosine squared is the same as secant squared, so that's it. So we can simplify it all the way down to this here. Questions on this here? If y'all do have questions, please ask. Not all of these steps are intuitive, but I can help you see some of them. Questions on any of this here? We have one last one. We want to simplify this here. And well, luckily enough, we're just going to use the distributive property. So we'll have cosine of alpha times sine of alpha. Well, that's just going to be cosine of alpha, sine of alpha. Cosine of alpha times negative cosine of alpha would be negative cosine squared of alpha. Negative sine of alpha times sine of alpha would be negative sine squared of alpha. And lastly, negative sine of alpha times negative cosine of alpha. The negative and negative make a plus. Sine of alpha cosine of alpha. Now, even though they're written in different versions, our cosine of alpha, sine of alpha on the two ends are the same thing. So we can say 2 cosine of alpha sine of alpha. Now, there is something interesting with our cosine squared of alpha and sine squared of alpha. They are both negative. But, and this is kind of just going back to this here, because if sine squared of alpha plus cosine squared of alpha equals 1, well, I could factor a negative out of both of these here, which would give me sine squared of alpha plus cosine squared of alpha. And this whole thing becomes 1. Oddly enough, that's as far as it goes, because we don't have any powers to replace sine and cosine, and replacing them as secant and cosecant wouldn't make it simpler. It would just give us a weird fraction. So that's as far as this goes. Any questions on any of this here?